my students and I work on very tiny robots. Now you can think of these as robotic versions of something that you're all very familiar with, an ant. Right? We all know that ants and other insects at this size scale can do some pretty incredible things. Right? We've all seen a group of ants or some version of that carting off your potato chip at a picnic, for example, right? But what are the real challenges of engineering these ants? Well, first of all, how do we kit the capabilities of an ant in a robot at the same size scale? Well, first we need to figure out how to make them move when they're so small. We need mechanisms like legs and efficient motors in order to support that locomotion, and we need the sensors, power, and control in order to pull everything together in a semi-intelligent ant robot. Right? And finally, to make these things really functional, we want a lot of them working together in order to do bigger things. So I'll start with mobility. Insects move around amazingly well. Right? This video is from UC Berkeley. It shows a cockroach moving over incredibly rough terrain without tipping over. And it's able to do this because its legs are a combination of rigid materials, which is what we traditionally use to make robots, and soft materials. Jumping is another really interesting way to get around when you're very small. So these insects store energy in a spring and release that really quickly to get the high power they need to jump out of water, for example. So one of the big contributions from my lab has been to combine rigid and soft materials in very, very small mechanisms. So this jumping mechanism is about 4 millimeters on a side, so really tiny. The hard material here is silicon, and the soft material is silicone rubber. And the basic idea is that we're going to compress this, store energy in the springs, and then release it to jump. So there's no motors on board this right now, no power. This is actuated with a method that we call in my lab, graduate student with tweezers. So what you'll see in the next video is this guy doing amazingly well for its jumps. So this is Aaron, the graduate student in question, with the tweezers. And what you see is this 4 millimeter size mechanism jumping almost 40 centimeters high. That's almost 100 times its own length. Right? And it survives bounces on the table, is incredibly robust, and of course survives quite well until we lose it because it's very tiny. Ultimately, though, we want to add motors to this too. And we have students in the lab working on millimeter-sized motors to eventually integrate onto small autonomous robots. But in order to look at mobility and locomotion at this size scale to start, we're cheating and using magnets. So this shows what would eventually be part of a microrobot leg, and you can see the silicone rubber joints, and there's an embedded magnet that's being moved around by an external magnetic field. So this leads to the robot that I showed you earlier. The really interesting thing that this robot can help us figure out is how insects move at this scale. We have a really good model for how everything from a cockroach up to an elephant moves. We all move in this kind of bouncy way when we run. But when I'm really small, my feet, the forces between my feet and the ground, are going to affect my locomotion a lot more than my mass, which is what causes that bouncy motion. So this guy doesn't work quite yet, but we do have slightly larger versions that do run around. So this is about a centimeter cubed on a centimeter on a side, so very tiny, and we've gotten this to run about 10 body lengths per second, so 10 centimeters per second, so pretty quick for a little small guy, and that's really only limited by our test setup. But this gives you some idea of how it works right now. We can also make 3D printed versions of this that can climb over obstacles a lot like the cockroach that you saw earlier. But ultimately, we want to add everything on board the robot, right? We want sensing, power, control, actuation all together. And not everything needs to be bio-inspired. So this robot's about the size of a Tic Tac, right? And in this case, instead of magnets or muscles to move this around, we use rockets, right? So this is a microfabricated energetic material, and we can create tiny pixels of this, and we can put one of these pixels on the belly of this robot. And this robot then is going to jump when it senses an increase in light. So the next video is one of my favorites. So you have this 300 milligram robot jumping about 8 centimeters in the air, right? It's only 4 by 4 by 7 millimeters in size. Right? And you'll see a big flash at the beginning when the energetic is set off and the robot tumbling through the air. So there is that big flash, and you can see the robot jumping up through the air. So there's no tethers on this, no wires connecting to this. Everything is on board, and it jumped in response to the student just flicking on a desk lamp next to it. So I think you can imagine all the kind of cool things that we could do with robots that can run and crawl and jump and roll at this size scale. Right? Imagine the rubble that you get after a natural disaster like an earthquake. And imagine these small robots running through that rubble to look for survivors. Or imagine a lot of small robots running around a bridge in order to inspect it and make sure it's safe so you don't get collapses like this that happened outside of Minneapolis in 2007. Or just imagine what you could do if you had robots that could swim through your blood, right? Fantastic Voyage, Isaac Asimov. Or they could operate without having to cut you open in the first place. Or we could radically change the way we build things if we have our tiny robots work the same way that termites do. And they build these incredible 8-meter-high mounds, effectively well-ventilated apartment buildings for other termites in Africa and Australia. So I think I've given you some of the possibilities of what we can do with these small robots. And hopefully we've made some advances so far, but there's still a long way to go. And hopefully some of you can contribute to that destination. Thanks very much.